These are your notes for section 6.4, and we're going to talk about the graph of ax squared plus bx plus c today, which is also called the standard form of a quadratic. Here's a journal choice for you. And here we go. The objective and what's the point? We're going to relate the graph of a parabola today to its vertex form, and we're going to talk about projectiles today. This is a really important lesson today because most of the time you will not see equations in vertex form, which we talked about yesterday, which is so nice and easy to graph. Instead, they give it to you in standard form, and standard form is a little more difficult to interpret, but it is nicer because you can type it directly into your graphing calculator. So we're going to try to work back and forth between the two forms today. Then we're going to talk about word problems involving quadratics, and the thing that's kind of exciting about what we're talking about today is the problems that you're going to look at today is really what caused the invention of calculus and most of the modern physics, the math of physics, I would say. All right, so here's some facts, and you probably know this, but many projectiles travel in a parabolic path. When you shoot a basketball, it's like that. It's a parabola. Okay, it's not a full parabola because there's a starting point, like where your hand releases. Same thing like with a baseball. When a baseball is thrown, this is going to be a horrible drawing. Let's see how I can draw this. Okay, there we go. And we throw the baseball, and it like kind of curves down towards the catcher. Yeah, it's so bad. That's kind of funny. Okay, a gun shoots at a parabola. And I'm not going to draw a gun on this because your parents might walk in and think that's odd. When people go hunting, the reason I'm thinking that is when hunters hunt, like bow hunting, that goes a parabola. It affects how they aim and stuff. That's why the sights are the way they are. But many different projectiles travel in a parabola path. Any equation of a parabola in vertex form can be rewritten in standard form. All you have to do is algebra. You just have to solve for y. So you have to expand the binomial squared and combine like terms. So that's what we're going to do first. We're going to write these equations that are in vertex form. We're going to write them in standard form. So the first thing you need to remember is that x minus 3 squared is the same thing as x minus 3 times x minus 3. Okay, so y plus 6 equals. We're going to go ahead and double distribute this. And I'm going to just go ahead and start writing up here. Y plus 6 equals x times x is x squared plus 3x. Oh, excuse me, minus 3x minus 3x, that's minus 6x, plus 9, subtract 6, y equals x squared minus 6x plus 3. So if I type this into my graphing calculator, I should get a parabola with a vertex at 3, negative 6. If I subtracted 6, that's where it would be. Okay? This one is a little more difficult to expand, but not impossible. Y equals negative 3. You're going to hold on to this negative 3 for a while because we're going to expand the x plus 5 first. If you do that shortcut we talked about, that's x squared, 5x, doubled is 10x, plus 25. And this plus 8 is kind of hanging out too. Now I will have to distribute the negative 3. Y equals negative 3x squared minus 30x minus 75 plus 8. Finish it up. Combine like terms. Y equals negative 3x squared minus 30x, 75, 70, 57, 67, excuse me, minus 67. Okay, so that's standard form. If I graph this, it would have a, would be frowning face first of all because it's a negative 3. And it looks like it'd be negative 5, 8 would be its vertex. So you could check that out on your graphing calculator if you don't believe me. Okay, the parabola congruence theorem says the graph of a standard form of equation is going to be congruent to the graph of just y equals ax squared. It's talking about those mother functions again here. So if I have that y equals 4x squared plus 2x plus 1, that's going to be congruent to the graph of y equals 4x squared. It's just going to be a shift of it somewhere. Okay? Basically, if the a is the same, this b and c stuff is just going to move your parabola. All this extra stuff is just going to move it and shift it. And if it was in vertex form, it would be very easy to tell. But basically, you're checking the a's, and you're going to see if they're the same. If they are the same, then the parabolas would be congruent. You could map them on top of each other. And you did lots of that in geometry. Okay, so we're going to determine if this parabola that we are given is congruent to, I don't know if you can read this, y equals 9x squared. All right, I'm going to switch up the ink to white here. I don't know if you can read this very well. So what I'm going to do is I'm going to expand this. Now, I don't have to expand it all the way because I'm really only concerned with the a term. So I'm going to do the shortcut method of expanding this. That's going to be 9x squared plus 3x double is plus 6x plus 1. I was done right after I expanded this because I see the 9x squared. This negative 6 is only going to affect my c. A is the same as 9. So are they congruent? The answer is yes. Now this guy I'm going to have to work a little harder at. So I have my y minus 6 equals 1/9 is going to hang out for a minute. I'm going to expand the binomial here. 9x squared, that's 81x squared. I do not need to finish it because that b and c stuff is not going to affect if it's congruent or not. You can, if this makes you uncomfortable to leave a problem and done like that, please do. Then I would distribute the 1/9 and I am going to get 9x squared. And it would distribute everywhere, but again, I'm not finishing that problem yet. So I have y minus 6 equals 9x squared something. There's still more stuff. But I don't need to finish it because this is 9. A here is a 9. This one is also congruent. It doesn't look like it would be. And some of you, when you got the 81x squared, would probably right away said, nope. But that 1/9 will really change things up when you distribute through there. Okay? Again, you can completely expand it if it makes you feel more comfortable or you're really just worried about that a term. All right, this is so exciting. And I'm going to be 100% honest. I was not a big fan of physics when I was in high school or college. And it's really weird for math people not to be. But science just isn't my thing. But this is interesting to me. We're going to read page 395. I had a copy here in the notes, but I don't think you can read it. I think you'll get mad at me if I make you read it. So I did pull out the book. All right. First of all, there's Sir Isaac Newton. He has nice hair, I think. I don't know if that's really pertinent to what we're talking about, but I just thought I'd mention that. And here's what I want you to talk about. Gravity is a force that pulls objects near Earth downward. Duh, you're all saying we know this. But without gravity, this is very hard for kids to picture. If there is not gravity, if I throw a ball up into the sky, it's going to continue traveling at a constant rate. It will never slow down. It'll just keep on zip, 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 up forever and ever. And we could figure out what its height would be because it would be where did I let it go, the initial height, plus that speed times time. So if I'm throwing it at like meters per second, it'll be every second it'll be traveling that many meters. So this is an example only. If I threw it at 59 feet per second, that is the speed I'm going to throw it at, from an initial height of 4 feet, it would continue traveling at 59 feet per second. And its height after t seconds is going to be 4 feet because that's where I let it go, plus 59 feet per second. T is in seconds here. That should make sense to you. So it'll just keep going up, 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 up. And if I wanted to know where it was in 10 seconds, you could plug 10 in there and figure it out. Okay, Galileo had shown that gravity pulls the ball downward. He's like, oh, look, this stuff is coming down. And I don't know how, I'm sure your science teacher could tell you how, he actually figured out how fast it comes back down. Okay? It pulls the ball downward a total of 16 t squared feet after t seconds. So if it's 10 seconds, it'd be 1,600 feet. Okay? This effect can be subtracted from that upward motion without gravity. So this is going forever and ever, no gravity, and then all of a sudden we say, hey, wait, there is gravity. So let's subtract the effect or the height of the ball since gravity comes into play. So if you put these together, this will tell you how high your ball will be in general. If I just start off 1, I could plug it in and figure out how high it is because this is considering gravity. Okay, the number 16 in the expression is a constant for all objects. This 16 is not special to my example. It's always going to be 16. And that's if you're talking about feet. And if you're talking about meters, it's 4.9. You're going to see this all the time in science and math. Okay, so basically, oh, not you, this one. This is where this formula is coming from. So here's what this says to me in short. A thrown ball has height this after t seconds. And this is an example problem. Okay. This equation is a special case of this equation, and you will have to memorize this bad boy. The height, I'm going to call it the height time formula, okay? Height equals, I'm going to write up here because it is a little hard to read. Height equals, now this negative 1/2 g, this is optional to memorize because you might optionally memorize something else instead. But negative 1/2 g t squared plus v sub o t plus h sub o. We use this sub o stuff all the time in physics and science because it's talking about time, initial time, like velocity at 0 or height at time equals 0. Okay, so this g is always the same. Some kids just 32, this is feet per second squared, or g equals 9.8 meters per second squared. When you take negative 1/2, the numbers that are going to show up in the equation are negative 16 and negative 4.9. Some kids just remember negative 16 and negative 4.9, t squared plus v sub o t plus h sub o. But if you want to, this is the actual formula, negative 1/2 g. But you could remember negative 16 for feet and negative 4.9 for meters if you want, instead of the 1/2 g. Okay? Basically, this t squared is almost always going to be there. And this t is almost always going to be there. And this h is not always going to be there. And you're going to read the problem to figure out what to plug in for v sub o and h sub o. You're going to see a lot of these from here on out. They will be on multiple tests. They'll be on your test this chapter as well. Okay, h is height, t is time in seconds. V sub o is your initial upward velocity. When you actually let go of the ball, what was the velocity? H sub o is the initial height. Where did you let go of the ball? And g is that constant we were just talking about. Okay, so here's a couple things you might want to not jot down in your notes. If an object is dropped and you don't throw it, its initial velocity, the v sub o, is going to be 0 if you drop it because there's no speed behind it. And if an object starts at the ground level, its initial height is 0. So that would be h sub o. Could be 0 if it started at the ground. Okay, these are fun. Yoko. She threw a stone upward at a speed of 10 meters per second while standing on a cliff 40 meters above the ground. Okay, so here's the cliff. This is a horrible picture. Here's Yoko. And she threw a stone upward. So it's like whoop, and then what does it do? Oh, it comes down. Do you see the parabola? It's cute. Okay, the speed is 10 meters per second. And this height is 40 meters. I always draw pictures on these. My formula is going to be h equals, because it says meters, I'm going to write down negative 4.9 t squared plus v sub o t plus h sub o. Plug in what I know. Initial velocity, that's this guy, it's 10 meters per second. Negative 4.9 t squared plus 10t. Initial height, 40 meters plus 40. This is the formula that's going to represent this parabola that Yoko has going on with she threw her stone. So what was the height of the stone after 3 seconds? Well, plug that in for t, and you can figure this out. H equals what? Okay, I'm going to break out my calculator here. 3 squared is 9. 9 times negative 4.9 plus 10 times 3 is 30 plus 40. 25.9. What are we talking about? Meters. Let's think about that in the context of the problem. In 3 seconds, the ball or stone, whatever, is on its way down. It's a little past halfway mark. So this is where it's at 3 seconds. I like to mark it on my picture in case they ask me more than one question. I can compare it to where I think it should be. So how long for it to hit the ground? And that's what I'm talking about. I can guess 4 seconds maybe because it doesn't have that much further to travel because this is the ground. But we are actually going to do math. Okay, I'm going to look for when the height hits the ground. So I'm curious when the height will be 0. 0 equals negative 4.9 t squared plus 10t plus 40. Okay, we are going to solve this. We are going to solve this by looking at our graphing utility, okay? You're going to actually type in y equals negative 4.9 t squared plus 10t plus 40 to your graphing calculator. You are then going to look at the table, the XY table. You are going to have to be changing your delta x, your table step, until you can get really close to 0. We are looking for when that stone hits the ground. And we are going to get really close to about 4 seconds. Okay. The other thing you could do is you could graph it and you could look for the x-intercept. If you want to do trace, you could second calculate 0. That would be another thing you could do. If you want a more exact, we're going to talk about how to solve that algebraically a little later this chapter. Okay, we're going to do this lab hopefully in class. It's a neat way to really see where the G constant came from, the 32 and the 9.8. So hopefully we can do that in class. And we'll finish that up. And here's the book assignment. Since we are going to do the lab in class, we're going to do 6-4B in class. Do go ahead and start this book assignment tonight if you can, and I will see you tomorrow.